Hi, everyone. Thanks for tuning in. We will talk about the architectural evolution that has happened in distributed training over the past decade, actually. So, today we'll explore how distributed training has evolved to keep up with the explosive growth in model size. The deep learning models have grown from millions parameters to trillions of parameters, and as models have scaled, so have the challenges. So, memory limits, communication, resource usage, all of these have some issues. And there have been many things that have been built to get around those issues, fix those issues. We'll walk through some architectural milestones from parameter servers to ring all reduce, pipeline parallelism, and zero. Along the way, we'll see how these advances work alongside optimizers like Lars and Lamb to train larger models faster and more efficiently. Let's begin. Between 2012 and 2020, model sizes skyrocketed. Single GPU couldn't just keep up. We needed distributed training, splitting work across devices, but that created new problems. Early systems used data parallelism. Each device processed a batch and synced with others. Sounds simple, but syncing meant a lot of communication, especially for big models. As GPUs waited on each other or the network, efficiency tanked. And the other issue was memory. So as models grew, so did the need to store parameters, gradients, and optimizer states. That meant memory often became the bottleneck, even with multiple devices. So then came in the parameter server architecture. And this was done, so this came in to coordinate multiple workers. The parameter server emerged, a central node holding the model. Workers would compute gradients and send them over to the server, which would then update the model. It had two sync modes, synchronous and async. In the synchronous one, all workers wait and update together, simple but slow. Asynchronous worker move at their own pace faster, but it doesn't optimize as good, and there are some inconsistencies. So while useful early on, the centralized server became a choke point. And you guessed it, because there was a centralized server. As you scaled to dozens or hundreds of workers, the server got overloaded, much like everything trying to exit a stadium through one door. Plus, it introduced a single point of failure. So we scaled up, the architecture started to fall apart. Then, early optimization challenges specifically stood out, and these were communication overhead, the frequent syncing of massive tensors overwhelmed the bandwidth, the straggler effect. So in the synchronous setup, slow workers held everyone back, like waiting for the last hiker in the group. And the third one, idle resources. So GPUs spent time waiting instead of computing, especially in mixed hardware setups. So we needed smarter ways to share data, memory, and manage the memory and keep the hardware busy. Then came in ring all reduce, which was basically a better way to sync. To get rid of the central server bottleneck, we turned to ring all reduce and imagine arranging all GPUs in a ring. Instead of syncing with a server, each GPU talks only to its neighbors. So gradients are passed around the ring, gradually summed and shared. This reduces network congestion and scales well. Each node does equal work, no bottlenecks. It's like replacing a traffic jam at one big intersection with a smooth flowing roundabout. How's that for an analogy? So, the result, better bandwidth use and near linear scaling. Add more GPUs and training speeds up proportionally and up to a point. Sound good? Next came in pipeline parallelism. This was basically done to fit bigger models. Even with ring all reduced, fitting huge models on a single device was still tough. That's where pipeline parallelism helps. We basically here in this approach split the model layers across devices. So GPU 1 handles layers 1 to 10, GPU 2 handles layers 11 to 20, and so on. You take the model, you divide up the layers, and hand them off to different compute nodes or GPUs. It's like an assembly line. Data flows from one GPU to the next during forward and backward passes. We use micro batches to keep all GPUs busy, just like feeding the items down the pipeline, so no station is idle. This dramatically reduced memory per device, memory usage per device, letting us train much larger models without hitting memory walls or memory constraints. Next came in the approach of zero. This was done to basically kill the redundancy. So traditional data parallelism meant each GPU would keep full copies of the models, of the model gradients and optimizer states. And it was, as you can see, it was wasteful. So zero fixes this by splitting those elements across devices. Now each GPU only stores a slice of model in data. So it's like dividing a textbook among students instead of everyone carrying all of them. This leads to 8x better memory efficiency and making trillion parameter models more trainable. So I would just go back to the analogy. It's like dividing the textbooks for a day across students. So history book is brought by a student, the maths book is brought by another student instead of all students carrying all copies of all the books, each student copying his or her copy of each book. So it led to a significant memory efficiency, and the models that could be trained got significantly bigger in size. It also didn't hurt performance. It's smart enough to fetch or share data as needed while keeping everything stable. So this was a good thing to come along. Now, next what happened was we enabled a large batch training, not large scale, but large batch training. So larger batch sizes increase efficiency, and faster training is achieved through bigger batch sizes, but they can hurt convergence if you're not careful. So there are two optimizers specifically designed for this. These are LARS and LAM. LARS are just learning rates for each layer based on the weight to gradient ratio. So keeping layers balanced during training. And then LAM builds on that with added adaptivity for deep models like transformers. So LAM is specifically there to help with transformer type models. Now, these models make training with 32,000 plus batch size practical without losing accuracy or spending weeks on tuning, frankly. So they are key to keeping training stable at scale. Next, communication optimization. Basically, less talk, more work. So even with good architectures, communication is still costly. So what we did was compress and quantize the gradients. Gradient compression was done, and it helps drop or delays communicating tiny values. And quantization uses fewer widths for each number, like JPEG for gradients. Both of these reduce communication without hurting accuracy if tuned properly. And the goal is to spend less time waiting on data and more time training the model. Sounds good? What did we cover? We covered communication optimization. Yeah. Putting in all together, what's the impact? So the impact is that the training time for the same size of model and the memory efficiency, the training time has come down with each one of these milestones that we covered, starting from parameter servers. For this reference, the model that has been used to compare the is the same model. So if we just had the earlier milestone of parameter server, and if this model is trained using that approach, the training time would be basically 30 a month, and the memory efficiency would be low. And with each one of these milestones, the training time drops and the memory efficiency increases. These numbers are not hypothetical. Thanks to these methods, trillion parameter models are now a reality, and they are powering cutting edge science, language models, and climate simulations. So, distributed training is no longer a limiting factor, it's a launch pad.